All yours.
Welcome and thank you for coming. We are the Turbulence tank advised by Dr. Anderson. I'm Garrett Finnegan, and these are all my teammates, Mark Matigli, Megan Hunt, Shannon Sowar Trenstrick, and Evan Longberg. Shannon's going to introduce us.
Alright, so a little background on why we're doing this project. Many of you may be unaware, but the population of oysters have been drastically decreasing. And it is important to note that 50 to 85% of the oxygen we breathe come from plankton, so it's important to take care of these organisms and acknowledge them. Now, our advisor, Dr. Anderson, has been doing research at the Woods Hole Oceanographic Institute on the effect of turbulence levels on larval behavior. And so in order to aid his research, he has enlisted the help of Grove City to build a tank to mimic the ocean turbulence so that he is able to study and produce experiments in a repeatable way. Now here's our turbulence tank, and just to highlight it a little bit on how it works, you have this plexiglass body that we can fill up with water. And now there's 8 different actuators. We'll talk a little bit more in the next slide about how these work, but in general, these are what create the jets that provide turbulence, so it shoots water into the tank. And these are connected back to a computer that provides the input. We have 4 actuators on the top and 4 on the bottom at different angles. So this tries to promote homogeneous isotropic flow, which basically just means we want consistent flow in all directions throughout the tank. In addition, we have some air bleed systems on all of the canisters, so that these are valves you can open up to try to remove air bubbles so that we have water throughout all the tank and there's no air that could skew our data. And we also have a drainage system here so that we can easily remove all the water at the end of experiments. Now here's highlighting the actuators and how they work. So we have subwoofer speakers that a computer sends signals through an amplifier. This sends different voltages, so different forces are applied in different speeds. And attached to the speaker is a drive shaft. Now with this drive shaft, we've attached an accelerometer so that we can measure the acceleration and integrate it and find the velocity and position of how that moves so we can get precise data. This drive shaft is in turn attached to a screw that is threaded through this rubber diaphragm. So when the drive shaft moves from the speaker, this pushes the rubber diaphragm, and that pushes water through the tank through an orifice that is attached here. So there are little holes that push the water through and shoot out into the tank. Now the basic principle of how the water is pushed through the tank is called zero net mass flux actuation. That's a really complicated term, but in simple ways it just provides so much force from the speaker that shoots the water through the orifice holes that shoot out into the tank like shrapnel. So that it shoots out so quickly that the same water is not allowed to return back in. Different water from the tank comes back in. This adds momentum to the fluid without adding any mass to the system. So there is a zero net change in mass of this entire system. And here's just a video of how the tank works. You can see the particles moving around in here. And remember that these are really small organisms, so that we don't want huge turbulence levels, but it does affect them. And then here you can see the orifice that I talked about with the nozzles where the water jets shoot out through there. And now Garrett will talk a little bit more about our goals for the project.
So we set off with 4 goals for this project. The first one being that we needed a repeatable, precise volume of water output per stroke of our system. We also need to accomplish a field-relevant range of turbulence levels. That means we can't have too much turbulence or too little, so that the oyster larvae can actually be able to swim in them and not just be thrown around. We also want to improve the control system so that you could just press a button and it'd play and calibrate itself. Previously, it had taken several days and you had to calibrate each speaker individually. And then we did various minor improvements just to increase the user-friendliness of the tank. So the first one was, how do we make a precise volume displacement of water per stroke when we're going at such a high rate? And the original design was from the 2013 team, and they used these rubber membranes that moved like this with the speaker. And so there were several problems. It had inconsistent volume displacement per stroke. It did not actually, this is a theoretical, but in actuality, it kind of bent and distorted, and it was very difficult to measure the exact volume, and it was different for all the speakers. The system also leaked. This rubber wasn't perfectly watertight, and through the center, there was a drive shaft, which would sometimes leak, especially as it aged, because this rubber did not age very well as it was in seawater. So we looked into bellows. Bellows are springy devices that are pretty small, and you actually have them around near you, so you can see them. They're springy devices that expand and contract due to an applied force, and this allows us to pump a very specific and precise volume of water per stroke. And then these also came with 3 important design considerations as we talked to companies. They needed to be watertight. We couldn't have any leaks. We need really good specifications so that all 8 were as identical as possible. And then we also wanted a plug-and-play design, so the bolt circle was the same, and so we could just bolt it straight into the existing tank. We didn't have to tear the whole thing apart and redesign it. So, as you can see from this picture here, there's several important parts. The threaded drive shaft connects to the speakers and is driven by the speakers. This threaded drive shaft connects down into this cap, which is welded shut, and so there's no water leakage. And then this flange with the bolt circle hooks right up to the tank, and then these are the corrugations of the bellows that give it its springy-like properties.
Yeah, so to decide what bellows would be optimal for our system, we decided to model the actual system using physics. So we just started with Newton's second law, the sum of the forces equals mass times acceleration. And so below here is the equation we developed and coded in MATLAB using a second order differential code. And so we have mass times acceleration equals, we have the driving force from the speaker, the spring force from the bellows, and then the fluid forces that come from the water around the bellows. And so the whole modeling this system, you can think of it as a simple mass spring oscillator as shown by this diagram. So you have the driving force from the speaker here as a function of time moving the mass. There's the fluid forces as a function of time opposing that, as well as the spring forces opposing that. And so when we were talking to bellows companies and filling out spec sheets, 2 big parameters that we needed to know were the bellows outside diameter, which I have labeled as OD, and the spring rate, which I have labeled as SR. And the spring rate can just be thought of as the stiffness of the bellows, and it's how easily it extends or compresses. But you can't, so we found out that for our system, we can't just give them any combination of diameters or spring rates. We need to know exactly what we need. And so there's some limiting factors that went into that. The first of which is the volume output range that we were looking for. The range we were looking for is 15 to 500 cubic millimeters, so that tests can be done at lower levels of turbulence and higher levels of turbulence. The next thing is the stroke, and the stroke is the distance that the bellows moves back and forth when the speaker force drives it. And so we actually decided that about 0.5 millimeter is the optimal stroke for our system. The last thing being the speaker driving force. We needed to calculate how much force our speaker could output so that we could vary that as well in our code to figure out the best parameters. So here are 2 different cases, 2 different plots from our code. The first case, I input a diameter of 1 inch and a spring rate of 30 pounds per inch. And here you can look at the stroke. It's about close to 1 millimeter total of stroke peak to trough. And the volume output is about 200 cubic millimeters. So then to compare that with the other example, I kept the diameter the same as 1 inch, but increased the spring rate to 40 pounds per inch, so that the spring stiffness was higher, so it will not extend or compress as far. And so you can see the stroke has decreased, and now it's about 0.5 millimeter stroke total peak to trough, and the volume output is around 170 cubic millimeters. And so doing things like this, varying the parameters, putting in different values really helped us narrow in on what were the optimal values for our spring rate and our diameter so that we could present that to bellows companies when we were looking to purchase them.
So once we determined what our varying design parameters were, and once we found out what bellows companies we wanted to contact, we had some decisions we had to make. We had to figure out how we were going to implement these new bellows into a design that was going to be our new actuation system. So in this, we went through varying design iterations to come up with the design that we ultimately have now. So to start, we went with a shaft coupling design, and a shaft coupling behaves similar to that of a bellows, where it expands as a means of generating the turbulence and displacing the volume. So we ordered a shaft coupling from McMaster Car, and with this design, we had to manufacture all of the parts besides the actual shaft coupling itself. So we ordered 3/16 stainless steel stock and machined it down to design a flange that you can see in the corner there. With the flange, it has a bolt circle pattern on the outside as a means of connecting the whole assembly to the tank and the canister itself. There is a center hole in the center of the flange that the drive rod goes through, and a pattern of 3 holes around to connect the shaft coupling to the flange. So the drive rod goes through the through hole, through the shaft coupling, and ends at an end cap that has a threaded through hole in the center to connect the drive shaft or drive rod to it. With this design, we decided to not implement it into the tank because it just takes too long to manufacture all of the parts and was too costly for how much it took. And ultimately, the shaft coupling itself was just too small and didn't generate the amount of turbulence that we were looking for. So the next design that we tried was the Sigmanetics bellows design. So Sigmanetics is a bellows manufacturing company that we worked extensively with to see if they had any bellows options that fit within our design parameters. So these are the bellows that you see in front of you right now. So with this design, they are it would be very similar to that of the shaft coupling design, that we would have to manufacture the flange and the end cap on our own. But with this, we ran into various design challenges. So we had no form of actually connecting all the pieces together to assemble the whole assembly ourselves. Since the bellows are made out of a material known as Manel, our Grove City machine shop does not have the capabilities of welding Manel, so they would not be sealed properly. So with the sealing, the water would leak through and would affect the way the turbulence was generated and how the bellows behaved properly. And ultimately, the bellows were just too stiff for our application. They didn't fall well in with the design parameters that we were looking for. So this led us to choose the design that we have now. So they are bellows from KSM, that is also a bellows manufacturing company. And the benefits to choosing this design was that it is a fully assembled bellows assembly. So they were able to supply us with 10 fully designed bellows assembly that we are able to just apply to the tank and see how they work. So they are made of corrosion resistant 3/16 stainless steel, which works well with our seawater that we're using. And since they are fully assembled, they are welded properly, so we don't need to consider any sealing issues that we might run into. There is a threaded end cap that is on the inside of the bellows that securely fastens the drive shaft. And the most ideal part of this assembly is the actual shape of the bellows. They are the right size and they displace the proper amount of volume that we are looking for to have a controlled amount of turbulence that we are generating.
Great. So now we are able to generate and output a specific volume. The problem is that each actuator is going to operate differently depending on the forces applied. This basically means is that we have no way of controlling our system or verifying that the system is actually doing what it's trying to do, which is output a specific homogeneous isotropic flow in the tank. So with that, what we wanted to do is generate a closed loop control system with accelerometers. So what this is, it's a system that basically has an input and output. So what we do is that we create a signal, a voltage signal, by a single generator. And this is sent directly into the actuators. And the speaker is going to operate at a certain frequency and do what it needs to do. From that, the peak to trough distance, or the maximum distance that the speaker is moving, is called the stroke. And that's going to push the water out of the jets and create the turbulence itself. But we don't know what's going on with that. We don't know how far it's moving or anything. All what we know is that we inputted a voltage into the system. So what we do with that is that instead of just, what we do is that we read the stroke and measure it using an accelerometer. An accelerometers only measure the acceleration, but we know from physics is that if we integrate the acceleration twice, we're able to get the actual stroke and the displacement that the speaker is doing. So with that, we then put that through what's called a PID controller. All what this does is that it says if the stroke is compared to a command stroke of what we're trying to target, what it does is that it says if the stroke is too high, it's going to reduce the voltage, which in turn goes through the entire loop, and it reads it again, and it verifies, am I at the proper stroke or am I not? If I'm not at the proper stroke, I need to keep on reiterating this program until I am at the proper stroke. And so this actually allows us to guarantee that the turbulence is at a repeatable level. So also with that, we wanted to verify that it's actually working. So on the right is a video of the accelerometer moving. It's actually moving at 30 hertz, which is 30 cycles per second. But this video is taken at 1,000 hertz. So it's actually extremely slowed down because we're seeing a bunch of images per movement of the accelerometer. Then with that, over here we have our command stroke, what we're trying to hit, then what we're actually getting out of the accelerometers. This was verified using a high-speed camera and just measuring and doing pixel measurements to see how much the accelerometer is moving. So with that, we have each of the speakers, we have each of the command strokes that we're trying to hit, we have each of the output strokes on what we're actually hitting, then we have the percent difference, which it honestly looks very bad. A command stroke of 0.2 and an output stroke of 0.22. The thing is, you have to remember, this is in millimeters. And so even though that percent difference seems significant, it's actually fairly close and fairly accurate. Now there are exceptions. You can see there's a negative 29% difference and a 23% difference, but we're fairly sure this is because of the accelerometer not being calibrated precisely, or just because of the speaker operating and just being very strange. So overall though, we're able to conclude that with few exceptions, we're able to be accurate within about plus or minus 0.07 millimeters, which is a huge improvement over the previous system. It means that we know that the control system is functioning as proper and is actually doing what it needs to do. With that, also, we know the program is able to adjust for each speaker. This is a huge improvement over the previous year's turbulence tanks, which relied on just sending a certain voltage. Instead of sending the voltage, we're guaranteed that we know what the stroke is outputted, which means we're able to repeat these experiments because if we just send a voltage, we don't necessarily know what the speaker is going to do. So with that, we're able to provide accurate control using the program, and also we're able to do repeatable experiments, which means it actually can be used for what it's trying to do.
All right, now that we can do repeatable experiments due to Evans implementations, we needed to do data to make sure that we could take and do consistent turbulence levels and make those turbulence levels uniform throughout the tank as best as we could. To do that, we needed to do something called particle imaging velocimetry, which is just a fancy way of saying we take a laser and we take a camera and we flash the laser and take a picture roughly about at the same time. There's some nuances, but then we get images like this, zoomed in on the particles on a sheet of a laser to see how the fluid is moving by putting particles that glow due to the laser, rather they reflect, into the flow. And this is what the camera gets. And really all that is just a sequence of images, and the computer kind of puts them together like a flip book and goes through them and measures one photo and then the next photo and compares the difference in position to get a velocity. And that's what you see here on this chart. This is a chart of the magnitude of the velocity of one such example of a PID data set. So once we took that data, it soon became very apparent that the turbulence levels we were getting were just too high. If you look at the tank, all 8 actuators are pointed in the center, and that means all the water jets were focused in one small area. The original jet was just straight holes. There was no dispersion other than small fluid jet dispersion. But mostly the water jets were focused to the center of the tank. Our solution was to make a dome nozzle to spread out the water being displaced by the bellows. And here we see orifice 3. This was our first kind of attempt to kind of fix it. Unfortunately, the holes were too big on the nozzle that we did. You can kind of see the nozzle as a dome shape right here. And we didn't get enough fluid force because the holes were too big. There wasn't enough pressure. Then we tried orifice B. And orifice B was a perfect nozzle, and it really spread out the fluid flow, as you can see by the velocity magnitudes. And it was just a great improvement from the original straight flat nozzles. Once we found that we could pretty much separate the flow into different areas of the tank and make it more uniform, we needed to have a set measurement to quantify how much turbulence was actually in different parts of the tank. And to do that, you needed to do some calculations and find what's called the Kolmogorov scale. And really all it is just the smallest size of little whirlpools in the flow. Now turbulence is just a bunch of whirlpools in a flow, and they slow down and shrink to smaller whirlpools. Now the Kolmogorov is just the smallest size of the smallest whirlpools. Unfortunately, it's kind of a back and forth process where we want the energy dissipation, which is this variable here, but we also need the Kolmogorov scale, which is here. So you kind of need to do some sort of correlational data analysis, or kind of just do some fluid simplifications to really be able to estimate it, and then go back and test and see if that's a reasonable measurement based on PIV data. So then to do that, we needed to have a correlational equation, and that's kind of what this is for the energy dissipation in the tank. And it looks really complicated, but all it is just how the velocity is changing in different ways. And once we had that, we were able to quantify different turbulence levels in the tank and at different places as well.
So, wrapping up our fourth and final goal, we want to do various minor improvements to the tank to make it more user-friendly. And here's one example. The previous air bleed valves were rusted shut because they didn't use stainless steel. So, we put these shiny new ones on. They won't rust as bad. We also use 316 stainless steel all around to prevent chemical interactions with our bellows. We used thin tubing and syringes to get up in there and pull all the water out, or pull all the air out. We fixed the transportation crate. We fixed the wiring harness. We machined accelerometer mounts and put those in. And then we used an optimal neoprene right here as a gasket to prevent the water from leaking.
Now for some finances. So the school provided us with $3,000 for our budget, but after extensive research, we realized there is no way that we could achieve what we needed and get bellows within this budget. So one important lesson we learned is that any budget can be broken if you ask for it in the right way. So we got a $750 extension of our budget. And as you can see from this diagram, even with that extension, the KSM bellows took up 80% of our budget, and everything else fell below 5%. And this Pareto chart just shows the price of each system. So the KSM bellows cost $2,950. So in total, we reached $3,710. So that left us with $40 to spare from our new budget. So thus, we were able to achieve all our goals in the deadline and the budget that we were given. Thank you for your time, and we are now open to any questions that you may have.
So, what would you say would be a surprise that you encountered that you just did not expect during all this work that you did?
The biggest one to me was probably how limiting our budget was. Most of the bellows, we talked to probably like 15 to 20 bellows manufacturers before we found these ones, and most of them were quoting us prices closer to like $60,000. So that was probably the hardest part.
Also, another surprising thing is just the level of turbulence. Because we're used to turbulence being a turbulent flow over an airfoil, which you can imagine that's very fast. The turbulence created in this tank, it's removing the water at a few like centimeters per second. So it's hardly even moving at all, you can see in the videos. So that's sort of surprising when you think of a turbulence tank, you think of a very fast flow.
What would be the next step if you continue the project? What's kind of on the horizon maybe for future improvements?
I know one of the big things is the control program. There's always more that can be done for that. There's more calibrations that you can do. There's a lot of testing that you can do in the tank. Even more with Mark, you can expand it a little bit more with the nozzles actually.
Yeah, and all the speakers they'll run at the same stroke, and so something that can be looked into is running the different speakers at different strokes to vary how the turbulence is working.
Yeah, just probably changing the nozzles to get a more uniform output. The dome nozzles were a really good improvement, but just the uniform actuation and just general turbulence level was more of our concern. So trying to spread out the turbulence was almost a second thought that just ended up helping, but still could be improved on.
So have some hot spots.
For the bellows that you created, was there were those just like the basic bellows, or were you able to give them specifications for that? And like, if you did repeat this process, you need to the spring rate, would you be able to like get that higher bellows for that?
Yeah. So whenever we contacted these bellows companies, they gave us like a huge list of all the specifications they wanted, and that's kind of what Trent was talking about with when we did the physical modeling to determine all those parameters.
So basically, I mean, it depends on the bellows companies, but we need, based off our budget, we needed to buy a stock bellows. So they already have predetermined spring rate, diameter, and so if you wanted to increase it, you'd have to see what they had. Because if you needed a custom-made bellows, that's when the price starts getting like really at hand. Yeah. So that was, and to kind of echo what Garrett was saying to the first question, that was like one of the biggest challenges was finding the specifications we needed, but also so that it wasn't custom-made, so we could purchase them.
8 bellows is a problem. If you wanted 100,000 of them, you'd get them for cheap.
Another thing to remember is a lot of these bellows are used in vacuum appliances and things like that. So actually it was humorous when we received the bellows. They were in a package with styrofoam. In the styrofoam there was other packages, and those packages had bubble wrap and twice vacuum sealed bags in addition to tin foil covering the actual bellows. So it's like, at that point, it's like the manufacturing and how these things are made, they're just a precision engineered part. So as soon as you have a precision engineered part, the cost is fairly high if it's not something that's already on the market.
How large of a region the volume do you need to conduct the experiments?
I'm not precisely sure. I know the laser sheet is only a few millimeters thick, and so realistically, when we're measuring only probably about, let's just say, 2 inches by 2 inches area with about a 1/4 inch thick at most. In fact, we want it as thin as possible because we're only measuring by 2D, but not 3D. So even then, the turbulence, in general, the homogeneous turbulence, we're just trying to get it turbulent all the same throughout the tank so that we're guaranteed what's going on in the middle is what's going on.
If you think about it, the nozzle shape graphs I showed that were the color charts, they're about like 10 centimeters by 15 centimeters, and that was really zoomed out just to get the shape of the flow. We take data much typically smaller than that.
Yeah, there you go. Yeah, typically the data is similar to this, which is fairly large, but we're only looking at the sample area. Other questions?
Did you look at any other, control blocks other than the PID loop for your accelerometers?
No, I've looked at the basic, the one that I looked at was just the proportional and integral control. The problem that I have with the system is that it's operating on about a 4-second update time. So because of that, I couldn't use derivative control because it wouldn't really impact anything. It makes no sense because the system is changing much faster than 4 seconds. That would actually relate to the question on things to be improved in the program, where how do we actually make the updates time more real time instead of 4 seconds. So we did not look into anything regarding other PID loops.
Thank you again, folks.